Right, well maybe that was the signal to start then. So, kia ora koutou everyone. Welcome to the University of Canterbury's UC Connect lecture series. These lectures are free, but we do ask you to register online to attend. We hope that you enjoy this evening's lecture and that you return to attend others. First, the housekeeping notes. So exits are on either side at the front and at the rear. Look for the green lights. And toilets are just outside this lecture theatre on the ground floor in that direction. If you hear the fire alarm, please listen to UC staff instructions and follow them out to the assembly point. Remain as a group. In the hopefully unlikely event of an earthquake, stay where you are and hold on. Do not evacuate unless instructed to do so by UC staff, in which case follow them to the assembly point. The format for this evening will be a 45-minute presentation, followed by 15 minutes for questions. Our speaker tonight is Dr. Clemency Montelle, a professor in the School of Mathematics and Statistics. Clemency began her university studies here at UC, taking mathematics, because she loved that at school, who wouldn't, and Greek and Latin because she was fascinated by classical languages and ancient texts. This, at first, seemed an odd mixture of subjects. It meant a crazy timetable and lots of running across campus to get between classes. However, it was during her fourth year that Clemency had a light bulb moment. While searching the library shelves for a particular Greek essay, she came across a copy of Euclid's Elements in ancient Greek and realised that she could read this famous mathematical text in the original language. Recognising that her two seemingly disparate subject areas could be combined led Clemency to an interdisciplinary career that combines ancient languages, history, and mathematics, and has taken her to many different places in the world. In fact, I believe she's not long off a plane from India. Clemency completed her PhD at Brown University in the USA as a Fulbright scholar. During her doctoral studies, she learned Arabic and Sanskrit. And her current research aims to reintroduce Indian scientific traditions into the history of science and to understand how India has contributed to science globally. Another important mission for Clemency is to make mathematics and the history of science more accessible to students. Her unique approach to mathematics is aimed at humanising the STEM subject and drawing in new students who might not fit the picture of the stereotypical STEM student. Tonight, Clemency is going to share with us a fascinating picture of the history of the number 0. Welcome, Clemency.
Many thanks, Philippa, for that kind introduction, and I'm really delighted tonight to be here to talk to you about, well, nothing. Indeed, I'll try to lay off the jokes and the puns on 0. So it's an elusive concept to some, it's found spiritual significance to others, it's bog standard numeracy for young children, it's a useful run-of-the-mill aspect for those who use spreadsheets, the threads of which we can trace all the way to ancient times for the very first literate cultures of inquiry. It's 0, but before we go way back in history to look at some of the earliest instances of what we call 0 and actually see if the hype that is behind 0 is indeed worth it, I want to take us somewhere a little more in the modern day times. So imagine a scene such as this, which can be just captured from recent promotional material off, say, our favourite bank, Westpac. I have this friend who has 2 teenagers. And as you can imagine, she tries to keep track of them by various means, secretly refriending them on Instagram, Snapchat, Discord, and all other aspects. And they don't realise, I think, that when they first opened the accounts, when they were back young, she's also tagged onto their bank accounts so can keep a check on their bank balances. So anyway, when she looks at these 2 teenage balances now and then, she finds teenager 1 has this balance here. we see $109.38, it's a healthy balance for a teenager. It fluctuates a little bit, but what I want you to notice here is this zero here, of course, happily sitting there. The other teenager's bank, this teenager, well, they are, any laughter from the audience is entirely coincidental from teenagers. It's a busy teenager, spending money as soon as it comes in, and their balance looks more like this. So what sort of zero do you want showing on your bank statement? This one? Or even more of zeros like this? Or this one? It leads us to believe that, in fact, when we think about zero, in fact, we can disentangle the notion of zero just a little bit more. We understand zero as a placeholder, just like in the teenager's bank account. This zero here says there is nothing here, or it's holding the place of the tens. We also, if we have really big numbers, 308,065, or if we are telling the time on our 24-hour clocks, we might say 1:45 in the morning is otherwise represented as this 0:45 here. So there's zero, which is really useful as a placeholder, given that we work in a very famous system that we don't even think twice about using anymore. That is our place value base 10 system. But there's also zero understood as an arithmetical operator, a bit like the zero that we see in the teenager's second bank account. That is, it's just zero is perhaps taking a number away from itself. I have 5 apples, take 5 apples away, I've got 0 apples. Or some of the operations of arithmetic that we can do with zero, we say 0 times 32, according to the mathematical laws that we have, is 0, or we might say 0 plus 8 is equal to 8. So the various arithmetical operations that we all agree upon use zero in this way. So there's simultaneously two faces of zero which can be seen as both mutually important together, but really, as we shall see historically, in fact, were two distinct things and can be viewed as two distinct things as we look at the various instances of them throughout history. Zero has led some people really to go a little bit, get a little bit excited about its significance. So you just look at the internet and you Google zero, and in fact, you'll find people calling it the God force, or this elusive quality, people who my obsession was finding this earliest zero, or people who pronounce our greatest intellectual achievement. Other things, a symbol that would become the very foundation of our number system, the very first zero. So people are starting to get a bit obsessed with finding this zero. And other such wonderful poetic ramifications of the zero. The number 0 in bold capital letters shouting at you resonates with the vibrations and energies of eternity, of infinity, oneness, wholeness, continuing cycles flow and the beginning point. So zero has provided really sort of poetically or intellectually stimulating for ways which often some of us might find a little surprising. Nothingness, emptiness, it's not null as it appears, but it's actually a boundless source of inspiration, creation, engagement, and ultimately happiness. So indeed, what is the big hype about? And in fact, it hasn't just gone into the spiritual or the numinous realm, but in fact, psychologists and neuroscientists have picked up on this so-called elusive concept. And we find papers published in academic journals which look at trying to test our sort of neuroscientific synaptic receptors to thinking about zero or nothingness more generally. So just whipping one off the internet, brain processes which lead to the concept zero on the number line. So the idea of a number line as being this middle. And in fact, this study actually hooked monkeys up to various brain measuring devices and gave them symbols, I think 1, 2, 3, 4, and 0, and showed compellingly, I guess, by the synaptic activities that monkeys were more likely to associate 0 with the number 1 than any other number. So take with that, and then they established the idea that the number line is something that is neuroscientifically hardwired into us. Really interesting, but does it actually say that there's something hardwired in human beings and indeed other members of the animal kingdom towards this concept of zero? Is it much ado about nothing as people quip? What is the big fuss? all about. Human beings love firsts, okay, and discrete activities such as the first man on the moon, the first automobile, the first person to climb the Himalayas, the first McDonald's, the first women's vote, the first Apple computer, and the first cell phone. If we're hardwired to anything, we love thinking about the first time. It's something as human beings that we like to celebrate. What I want to question a little bit for you tonight is, does it make sense when we're looking at historical cultures and different cultures of inquiry, all who have specific intellectual ways of doing things, ways of counting, ways of enumerating, ways of forming mathematical concepts? Chinese scholars in history have showed us that they have specific ways of doing mathematics which are quite distinct for those in the Islamic Near Eastern traditions, which are quite distinct from those again in, say, the Indian traditions, which are quite distinct in turn from the traditions of ancient Greece. So does it make sense when we're dealing with intellectual flourishing of cultures and concepts within there to actually try and say, there is a first time for this idea? What I want to hope to leave you with tonight is that 0 is nothing without its associated number system. That is, you can't hunt for 0. The bigger and more interesting question in the history of mathematics is indeed to think about the ways in which early peoples and intellectual cultures of inquiries have thought about number more generally. And 0 is an important, but just a part of that more generally. So we will go back in time and let's look at some various ancient systems of numeration and see the ways in which 0 manifested itself and whether it was even a necessary part of the particular cogitating about numbers that ancient people had. So we'll go back to the very earliest literate culture, the ancient Near East. I'm going to get you to do a little bit of mathematical work tonight. I bet you didn't know you were going to sign up for that. When we look at one of the earliest forms of mathematics. Now, the wonderful thing about the ancient Near East, and because we'd be talking about our sources and how far in time our sources are removed from the original time at which the people were living. The wonderful thing about the ancient Near East is we're dealing with artifacts which are original to the time in which they were produced. So this is a cuneiform tablet. It's a beautiful transcription where somebody has taken this, which is usually fired. It's made out of clay, so it's indestructible, and it's meant that these artifacts have lasted for almost 4,000 years. So among the wonderful tablets that we have many that are mathematical, and here's one of them tonight. And little did you know, you'll leave here with actually knowing how to do some cuneiform mathematics. So if we look at this tablet carefully, and we'll see that indeed they look a little bit like chicken scratches, some scholars have likened them to, but these are wedges impressed upon clay with a stylus. Now if we look at the first column here, we'll see we have one such wedge impression, all right? This is the wonderful thing about reading historical mathematics, is once you've picked up a pattern, you can be pretty sure that you can get confirmation that what you're reading is correct. So we've got one wedge here down, if we just look at this column here, and indeed because it's an artifact, we have two sides of this, the obverse, just like we might call with a coin, and the reverse, which is the other side. So we've got one wedge here, and underneath it we've got two, good, and underneath it we've got three, and then what do we expect? Four, and you can see nicely this way of numerating is that we get three little wedges which become squashed up and we just zip round the bottom to do our number 4. And then continuing on, we've got the number 5, and then the number 6, and then what do you expect is going to happen once we get to our 3? We flip down, excellent, and we get our 7, our 8, and our 9, and then what do we have? What do we expect here? 10, excellent, that's exactly what we've got here. So we've got a symbol for 1 which gets repeated 9 times until we get a new symbol which is actually achieved by taking your stylus and just impressing it in rather than an impression and a flick. And then as we imagine, we've got 10 and 1, which is 11, 12, 13 and 14, and so forth and so on. I'll leave the other half of the tablet to you. I've got some copies here if you want to take one home to read it later. All right, column 1 is easy. So we've got we've got the numbers from 1 to 14. What about this other side? Just have a little think about what you've got. What do we have here? 9. What do we have underneath it? 18. What do we expect to have underneath that? 27. What have we got here? 36. What is this mathematical pattern it's telling us? It's a times table. One of these earliest mathematical texts is in fact this wonderful 9 times table, all right? So 1 times 9 is 9, 2 times 9 is 18, 3 times 9 is 27. Of course, we have no symbolism. There's lots of wonderful things we can conclude about this mathematical cultural inquiry, which we won't have time to look at now. But here's what we've got. Wonderfully speaking, 4 times 9 is 36, 5 times 9 is, and so forth. Now, what 6 9s are 54, 7 9s, what do we have here? We want 63, right? But we've got a 1 and we've got a 3. Next line. 8 9s, what are 8 9s? But what do we have? We've got a 1 here and a 12, all right? And so forth and so on. Can anybody figure out what's going on? It's base 60. And this, we can say, the earliest literate culture in human history reckoned their numbers not in base 10, but in base 60. And if you ever get confused, we still have vestiges of it today. In fact, it's a major part of how we count today when we reckon hours and minutes. So base 60, the very first form of numeration in human history, in fact, still survives today. So why is this important? Well, where's the 0? Do we need a 0? Okay, so if we just look. So 1 and 3, literally you can think of about 1 hour and 3 minutes, or 63. 1 and 12, think of it as 1 hour or 60 minutes, and 2 so 72. So all of our powers here in base 60. When we get a number bigger than 120, it's just 2 lots of 60 plus our 6. So where's the 0 here? And in fact, we ask ourselves that interesting question because, of course, we don't need one. We don't need a 0 here because we have a symbol for 10. We don't need one for 60 because we just use this number 1 here. We don't, in this system of numeration, when we are counting, we actually don't need that place holding 0 at all. Our numbering system is taking care of it. Where did we find these tablets and hundreds and thousands of tablets like this? Well, indeed, we find them in what we call the ancient Near East, or otherwise known as the Fertile Crescent. Why? Because we've got these 2 rivers here, the Euphrates and the Tigris, which provided this crescent shape, very fertile area for farming to take place. And we've got, some of you may have heard the famous Uruk and Kish and modern day Baghdad here. It's loosely southern Iraq today. And in fact, the fascinating thing is until 150 years ago, we had absolutely no idea, except for passing references here and there in very ancient literature to individuals from this region, that British and French explorers went through this area, found these big mounds and found the remains of ancient cities, dug them up and found hundreds and thousands of cuneiform tablets, which had epics and laws and temple records and palace archives, and along with them, hundreds and thousands of mathematical tablets, almost all of them in the base 60 that we've seen today. So we see this base 60, or sometimes it's called sexagesimal. We've got here, though, an embedded base 10. And when I say that, I mean we've got a symbol for 1, a unit, and then a symbol for 10. And it's a positional system. That is, there's a certain amount of ambiguity, we might like to think about it, in that we aren't able really to express an absolute magnitude of a number, but rather only a relative one. But it really doesn't matter. For instance, see this little one here, which you told me with absolutely no hesitation, this was to be 1. Similarly, for this down here, which is exactly the same figure, you told me this one has to be 60, all right? It's the same symbol, but where you put it gives it a sense of its magnitude, and context is very helpful for telling us. So 0, in terms of this, is very unnecessary, or even we might say irrelevant in this numerical context. We simply don't need this placeholder given the symbols that we've got. However, when we do look at some of the literature, we do find some evidence of place-holding markers. Here we have, indeed, an astronomical tablet. So we have a good idea, and in fact, what this tablet is columns and columns of numerical parameters, which are ultimately asking the question, when will the next first visibility of the lunar crescent be? So it's a non-trivial astronomical feature to compute, and to do so, many different columns of numbers are required. And you'll see that because we're dealing with artifacts that have been buried under the sand for almost 4,000 years and beyond, some of the tablets are in disrepair. Their surfaces get smudged off, they get smashed or damaged, or they're very piecemeal. So we understand the numerical patterns that we see in these columns. So we have an idea, just like you had for the 9 times table, how we should read the next number, because scholars have established the patterns, even for something as fragmentary as this, just given we have a good idea of the corpus. So in fact, what we have is a tablet that dates to the Seleucid Empire, which is the early centuries just before the beginning of the Common Era. And we have here a number which we know must be represented as 20 followed by a 7. And you can see now with your newfound knowledge of reading cuneiform symbols that indeed we've got this 20 here, and we've got this funny little 2 dip marks here, and then we've got our 7. And this is one of the instances of a scribe who is preparing this tablet telling us, don't smush them together and read them as 27, but rather read them as 20 followed by a 7. And it's a similar thing, just like we saw 3 times 9 was 27. You were very convinced and happy to read this as 20 and a 7. But this one here is telling us, do not conflate these two. These are 2 separate place value markers. So it's often said that in absence of sort of a round 0 type thing that many people are looking for, this shows a great facility on the part of these ancient mathematicians for understanding the notion of a place separator, just like the 0 in the teenage son's $109 in his bank account. There's other evidence that we have in the ancient Near East for 0, and this is a tablet from the Library of Kish. So in fact, we found this wonderful archive of various cuneiform tablets. And this tablet, and I have the whole thing there here if you want to come and look at it afterwards, is a delightful tablet. It was perhaps beyond what might be practical or answer a practical question, as most mathematics of this period was directed on. It's actually a table of numbers and their squares, and these numbers start at 1 and go up for every half up until 60. And so this is just an excerpt from it, but what we see is that we see along here, we've got the numbers that are to be squared and then the square of the number. So for instance, for those of you who can see, there we have the number 15, and if you take 15 and you square it, you get 345. Okay, just think, imagine 15 lots of 15-minute segments, I suppose, if you were trying to add up time, but if you express the square of 15 sexagesimally, you'll see it's 345, which you can just see just above that red line there. Similarly, if we look just below what I've circled, we've got 16 here. Now, if we take the square of 16 and we express it sexagesimally, I've just put the wee comma here for my modern way of indicating successive sexagesimal places, we get 4 and 16, which you can just see, here's our 4 here and our 16. Now, if you take the square of 1530, which is otherwise known as 15 and a half sexagesimally, we find that we need a place holding 0 between the 4 and the 15. So if anybody's looking for a place holding 0 in very early times, as early as the 8th century BCE, you will see it's right there, and it looks a little bit like the number 30. So there we've got 4, and then we've got these 3 wedges here, and then the number 15. So this is the scribe's way of indicating this place holding 0, and we know this has to be the case because the need for a place holding 0 in this tablet which has 120 entries, occurs 6 different times. So it's not a mistake, it's not a whim. The scribe has deliberately chosen these 3 little strokes here to represent a place holding 0. So this is as early as the 8th century BCE. So there it is there, these 3 little dips here. So if you're looking for the earliest 0, this is pretty much conclusively it as a placeholder. We also see in astronomical texts, and looking in some other instances, sometimes we find the idea of 0 just represented as an empty space. So for instance, I was telling you about these astronomical texts which use all of these columns to compute cumulatively the date and time of the visibility of the next crescent. This is a column here which is a correction, which is sometimes a negative quantity, but sometimes it's 0. And you can see this is a transcription of the tablet, but if you look right here, there's just empty cells here. So just like if you were using the Excel spreadsheet and you just wanted to put nothing there, you might leave the cell empty. This is exactly what the scribe has done. So don't tell me that the scribe's understanding that there's no need for that, you know, neuroscientifically there's something inferior about these scholars. They knew very well what they were dealing with when they were looking for 0. They also express it in words, okay? Here's a phrase out of the so-called procedure texts associated with these tabular, or these ancient spreadsheets, if you like, which says nutuk, which means nothing, u3, which means and, 10 ninda. Ninda is a sort of a metrological unit in Akkadian. Gargar, you accumulate nothing, and 10 nin. So there's a sense there, if we're remembering these 2 faces of 0, that in fact, here is a statement of 0 being used as an arithmetical operator. And again, these are in the few centuries preceding the Common Era here. That 0 is important, seems to be also used by these who, when they have to figure out some sort of way in which to incorporate this column into later computations, they always avoid ever multiplying by 0. Okay, so there's a slightly different computation going on to show that there's a sense in which 0 is treated as an arithmetical operator and needs to be treated differently than just other numbers. So there's 0 in the ancient Near East. So we've got definitive evidence that indeed we see it as this placeholder, albeit these cuneiform symbols that we see. In the Mayan civilization, which is not my expertise, but just in comparison, we see this is a vigesimal system, or base 20, interestingly enough, in which we have 3 distinct units: the shell, okay, which can be expressed for 0, a dot, which is 1, so these get just like our cuneiform wedges, we get 1 dot is 1, 2 next to each other is the number 2, 3 in a row is 3, 4 in a row is 4, until we get to 5, which we get this 3rd symbol, this straight line, and then building 6, 7, 8, and 9, and then 2 of these bars for 10, and so forth and so on, up to 20, which is the shell symbol for 0, because it really means 0 in any of the places from 1 to 19, and 1 in the 20th place, just like we saw 1 could be represented like 60 in our cuneiform tablets. So we see 0 in this civilization, indeed also very, very early in human history. And we can see this at play in various sources. And indeed, we've got to remember that sometimes the date at which the sources that have survived that come to us are usually much later than actually the systems were developed and refined and matured. So in fact, there's some debate is the exact application of some of these pictorial numerical systems that we find on this wonderful codex that has been preserved from the Mayan civilization. But what we can be sure about is there's certainly a placeholder for our 0 here. So for instance, we can read this number as 1, because it's 1 dot, 1 for another dot, then 0, then 6, and then another 0. So there we have this placeholder again. And the next one along could be understood as 10 here, that is 2 bars of 5 each, give us 10, 15, and then 0. And similarly, 9, 7, and our 0, and the like. But that we see, this little symbol for 0, hopping up in these numbers shows that indeed this placeholding 0 is just no big deal for the Mayans either. And they had a symbol for it and used it with the facility, even though we can't be sure exactly what these numbers have their practical application for. Maybe calendrical scholars have said it, maybe some planetary model for predicting where planets are, but we just can't be sure. When we see 0 in ancient Greece, okay, we've got two distinct forms of notation. So you notice when I'm looking for the earliest zeros, I'm actually taking you to answer the question, what does their system of numeration look like? And do we need a 0 there for it? But we see two systems in ancient Greece. One's called acrophonic. Phonic means sound, of course, and acro means beginning. So this is, of course, the antecedent to Roman numerals, but it takes the letters or the symbols which represent each particular number in this ancient Greek alphabet or system of numeration are indeed representative of the number. So for instance, this is the big capital delta. Some of you might remember this from your mathematics days, which deca is 10 in Greek, so they've used that for the 10. And then we've got hecaton, which is 100, so we've got this H sound here, and kilioi, 1,000, and the myriad, 10,000 here. So it's this lovely alternating system, just like Roman numerals, between base 10 and base 5. Okay, a symbol for 1, for 5, for 10, for 50, for 100, for 500, and so on, just like we know Roman numerals to be. Do we need a 0 here? You'll notice when I'm translating them into our, Indo-Arabic system of numeration, I've got zeros all over the place, but there's no need to develop a 0 symbol for this system of numeration in terms of needing a placeholder, all right? The other system that they have in ancient Greece just uses their alphabet. So just like we use X, Y, and Z in algebra, the Greeks used alpha, beta, gamma to actually represent numbers. So you'll see all 24 letters of the Greek alphabet representing a number. So alpha, beta, gamma is 1, 2, 3. Delta, epsilon gives us 5. And then we've got zeta, eta, theta, iota. Kappa, lambda, mu, nu, psi, omicron, pi, rho, sigma, tau. Upsilon, psi, chi, psi, omicron. So, and we've got a couple of letters here. This one here, which is otherwise known as stigma. This one here, which is known as a copper. And this one here, which is a sampi, which are very old Greek letters, which suggest that this system, which we can say for sure we have evidence of from the mid-5th century, arose even earlier given the archaic nature of some of the symbols used to represent this number system. But what's really interesting about this is alpha is the number for 1, but that has absolutely symbolically nothing to do with the number 10. We just use the next Greek letter in the row. So do we need a 0? No, it's the peculiarity of the system because it's not place value, it's the quality of the symbol that you choose that gives the number its absolute magnitude. Similarly, we don't need any zeros to represent 100, nor 200 or 300. We just choose successive letters of the alphabet to represent our numbers. So it's a little bit scary for us really because indeed, as happens, you get to a certain amount and you've just run out of symbols and you stop being able to count anymore. And the Greeks got up to 10,000 and then said, now what? And one of Archimedes' many great achievements, along with all the physical inventions that he has, were to come up with a system which allowed the ancient Greeks to count above 10,000. But do you need a 0? You don't need a placeholding 0 here. The number system is such that it takes care of itself. So to ask for a 0 is really to ask for something that isn't really appropriate for the mathematical environment in which the ancient Greek mathematicians computed. But we do have some evidence of this 0, 0 as an arithmetical operator. And we have evidence that it was produced at the time which we can be a little bit more secure of dating it. Greek papyrus is wonderful because the medium is such that it can survive even to the present day, albeit in very fragmentary form, as you can see. But here we have, again, another table, mostly with numbers on them, and scholars have laboured over finding the patterns and can say for sure that following this pattern here, here's some Greek numbers here, here's the number iota, which is 10, and theta, which is 9, so we've got 19 here. that this right here is a 0, okay, on a papyrus which has been dated to about the 2nd century of the Common Era. So you can see it's a wee circle, so it's looking a little more familiar to our modern eyes, but it's got this line over the top so as not to confuse us with this letter, otherwise known as Omicron, which actually represents 70. So if you see zeros in some of the Greek manuscripts, don't get alarmed, they are not zeros. This was not just one papyrus that was found, this was not just the whim of some scribe who decided he'd come up with some amazing invention or discovery, but rather we just, scholars have laboured through all these papyri and actually found that this symbol, that is a small circle with a line either on the top or kind of almost at the top or sometimes below, was not just an isolated event, but we can find it in lots of papyri, and you can just see the similarities, but also the lovely diversity in representing this number by ancient scribes. And we're talking about 500, 600 years gaps. You can see this symbol here was found in one that's in the 100 AD, this one here, 293, a little bit later, and there are some earlier ones there which I can't pull out here, and the like. So, the interesting thing about this 0, though, this sort of absolute value of 0, is it's always found in sexagesimal contexts. The ancient Greeks did astronomy, they used sexagesimals, just like their ancient Near Eastern colleagues, and it's always in astronomical contexts. We don't find this representation outside of astronomy. So this is sort of a 0, albeit understood in a specific context. The other place we do find it, though, is in works that were written around the first few centuries of the Common Era. Some of you will have heard of a famous Greek astronomer called Ptolemy, who wrote a wonderful work called the Almagest. And in the Almagest, and this was written in the 2nd century CE, but we don't have any manuscripts surviving from that time. It's just, you know, the harshness of the environment means that manuscripts just don't survive. The oldest one that we have, which is in the Bibliothèque Nationale, is from the 9th century. So we're talking about 700 years difference between the original text and the later text. But here we have, in fact, one of the first trigonometric tables in human history, or more properly, it's a precursor to a trigonometric table. It's in fact a table of chords. But what we see here is a peripherion, which means the arc or the angle. Okay, and we're going up by ½ degrees here. Remember our alphas and our betas and our gammas, which mean 1, 2, 3. And our oitheons, our straight lines, or our chords. And what do we have? This little 0 symbol with a line over the top. And we see it all over the place. This is an interpolation column to find a value which has not been tabulated. So there's 0 with a line over the top, so as to prevent you any ambiguity with thinking this is Omicron, that is 70, is seen in this 9th century manuscript. So we assume that in the process of making copies of manuscripts right from the 2nd century CE, that there is some continuity of tradition in the ways in which 0 was captured by these early scribes. So there we have it, albeit the 9th century, but we assume, and probably with good reason, that this practice is indeed centuries old when we look at these manuscripts. And now lastly, coming to an area, 0 in India. India is famous for many things, but most properly for indeed, finally we get into familiar territory when we're dealing with our number system. It's India that gave us those familiar 10 little glyphs from which we can represent any number whatsoever. It doesn't matter how big it is, be it bigger than 10,000 and the like. So there's 10 little, and it's also place value, which means straight away we're going to need some sort of symbol to hold the place in particular contexts. And we see that this is probably quite an old facet. So just, this is indeed a lovely insight from a commentator on a much earlier philosophical text, which says, just as a line, so a stroke, in the hundreds place means 100, in the tens place 10, in the ones place, so one in the same woman is called mother, daughter, and sister by different people. So there we have really encapsulated the idea. It's the place you put the symbol which gives it its meaning, not the symbol itself that we've seen in those other ancient cultures. And in fact, by the end of the first millennium of the Common Era, we see these lovely glyphs in Devanagari, the language in which Sanskrit, the ancient language of India, was written in. You've recognised some of them: 1, 2, 3, 4, 5, 6, 7, 8, 9, and then this familiar 10, which of course is a mixture of the stroke in the 10 place and this place holding 0. And of course there's no qualms by this stage about putting zeros, place holding zeros, wherever we need them. But we assume, given that these commentaries were found as early as the middle of the first millennium CE, that in fact people by this stage didn't think twice about putting place-holding zeros, that it must have been related to a much older practice. So we can say, it doesn't surprise us that this practice originated in the beginning of the Common Era to put these zeros, even though these manuscripts are much later, because manuscripts just do not last, especially in the temperate climates of India. What does last in India, however, if we think about manuscript evidence, are inscriptions. And inscriptions are done typically on stone, which lasts forever, or copper or brass plates, and they're actually inscribed, and you'll find them in various temples and pillars all over India. And we have here an inscription from a temple in Gwalior in Madhya Pradesh in India, which we can date around the first millennium BCE. We can do that based on paleography and other reasons, but we'll see here, if you look, it has on it a number here, 270, all right? So this is our first instance that we can concretely see as a place holding 0 on the Indian subcontinent, even though we can't date it properly, but it's contemporary with the people who are doing mathematics, that's we can be sure of. We see as we look outward for other Indianized countries in South Asia, such as Cambodia, we have this stone stele inscription, which we can date precisely because of this little inscription here in Old Khmer, which actually says the Shaka era, which is a particular era, just like we have the Christian era or, and the like, reached 605. So here we go, 60, that's that wee dot in there, 5 on the 5th day of the moon. So this one is of particular interest to many historians because they can precisely date, here is a 0 and it was written on this particular date here. So this one is lovely and still survives to us today precisely because it's written on this indestructible material. But that's so much for place holding 0, that first type. What about 0 as an arithmetical operator in Sanskrit sources? And we see texts as early as the beginning of the middle of the first millennium of the Common Era, some fairly sophisticated verses, albeit in a form of mathematical poetry, which really testify to understanding about 0. Here's an excerpt from a famous mathematician in India, Brahmagupta, with his text called the Brahmasputa Siddhanta. And you can see the sum of two positives is positive. These are just, lists of arithmetical operations. Two negatives and negative, of a positive and negative. The sum is their difference, so just basic arithmetic. If they are equal, it is 0. So there's 0, very much understood as an arithmetical operator, and it's got names. It's known as shunya, ka, or viat, which are all synonyms for the word void. We also see, and perhaps, again, it's a little bit later, but just so I can recite this, these are all meant to be memorized as these rules, these mathematical rules, because for the most part, intellectual activity in India was meant to be memorized and repeated orally because of the veneration of the spoken word over and above anything that you could write down or in a book. So here we have a lovely little verse which has a certain metrical pattern and a little bit of a tune to it. It goes, Vadadal viat kasyakam kenagate kaharo bhavet kenabaktasharashihi. And what it means, you can see it's got this metrical pattern, just like Humpty Dumpty or other little poems that we know. And multiplication and so on of 0, 0 results. So a number multiplied by 0 is 0, and square root of a number is 0. The square of a 0 is 0. So all of those are understood. There's 0 defined very clearly as an arithmetical operator, and multiplication by 0, 0. So that's always suggesting there's the understanding at this point, and this scholar, Bakhshali, but scholars earlier as well, about the commutative properties of multiplication. Very interestingly, and some of you might pick up on this, a number divided by 0. Of course, if anybody ever wrote that in a script in my calculus class, of course I would be like putting my red pen all over it. You can't divide by 0, at least we say. But what they say here is a number divided by 0. They call it kaharaha, 0 divided. It's as if these scholars were understanding the ideas of indeterminate forms that we look at today when understanding that dividing by 0 might be the same as dividing by very little numbers or taking limits or the like. So quite sophisticated arithmetical rules. So there's a very good understanding of the arithmetic. But just to close off, let's have a look at one of the most important manuscripts which can also pull some of the first zeros back further to find this elusive. What's the first 0 and how can we date it? And this is the Bakhshali manuscript, which again is important because this is another instance of a manuscript which is contemporary at the time that was written. It survived to us from the day it was written. But as you can see, because it was dug up by some agricultural labourer in the Punjab who was digging for stones, you can literally imagine he's there with his pickaxe, smashing through stones, and suddenly finds this manuscript buried on the earth. It's in pretty deplorable form, okay? Still, even these little bits, of course, are of huge interest to mathematicians to help us reconstruct exactly the mathematics that we find there. What's important about this is that it contains about 70 folios or pages of mathematical rules and examples, and it's been dated to around the 7th century, the original text, and this particular version of it perhaps as early to the 8th or the 12th centuries. We can do that because we're basing it on paleography. That is the script that's been used. It's similar to the other writing at that time. The language, the dialect that is used, and the content that we find. But what's really important about this date is that the Bakhshali manuscript is filled with zeros. So the date suddenly becomes of huge importance for those searching for this elusive concept of these zeros. Here you can see them here. Here's some numbers here. You can see 0, 0, 0, 0. Here's some more over here. The manuscript is full of zeros. So the Bakhshali manuscript is currently in the care of the Bodleian Library. And just a couple of years ago, they decided to send it to the radiocarbon daters. And they got some very surprising results. They took 3 sheets from it, took a tiny little fragment of the birch bark manuscript, not the ink, and that might be a problem, and they said, this particular page we date from this particular time period. The very next page is at least 300 years afterwards, but possibly even 500 years afterwards. And this page here was, as late as almost the end of the first millennium BCE. The results were absolutely confounding, okay? Given that technology and radiocarbon dating is of huge excitement to historians of mathematics, still these results really confounded us because they flew in the face of everything we knew about this manuscript. For instance, the results the Bodleian came up with suggested that this page and this page were as much as 500 years apart. What's really odd is even for the untrained eye, really there doesn't seem to be that much difference between this hand and this hand. So are they suggesting that somebody came along 500 years later and tried to mimic the exact handwriting, and not only that, kept the problem that ended with one word and picked up in another word in the next page? So these results were really confounding to us. But because they dated this manuscript so early, they could say that these zeros are as early as the 2nd century, and thus the earliest 0 that we have appears on this Bakhshali manuscript, which we know isn't true. We've seen it in the ancient Near East, we've seen it on Greek papyri, and earlier still. But what's very interesting is that it may be 0 as a placeholder, but some of the computations assume that they must have understood how to arithmetically operate with zero as well. So the two faces of zero are very much realised in here. One of these sheets has this big long multiplication on it with lots of zeros on it. Now, if you don't know how to do the arithmetic of zero, okay, that is, we do long multiplication, but however they did it, you're going to have to do multiplying by zero, you're going to have to add zeros and the like to be able to perform this multiplication. So zero in this Bakhshali manuscript is understood both as a placeholder and as an arithmetical operator. And we can niggle about the details. It seems that, in fact, even if it's just a place holding zero, it's no different from what we expected from other cultures. We've seen these place holding zeros in the ancient Near East, in the Mayan civilization, even in Greek papyri. So really, even if it is that early, it's of no revelation to us, but really confirms what we already knew. But we also want to argue that indeed the zero that we see there is not just a placeholder, but a fully understood arithmetical operations for which to use in computations. So to sum up, zero, what are we looking for? Given that we're based on textual sources, some of which occur hundreds of years after the original, what can we speculate about this world first? What I hope you take home tonight is really the idea that you can't look at zero, or you can't search for zeros outside the idea of looking at the entire number system and how zero fits in, both in terms of zero as this placeholder, just like one of these teenagers' bank account, and zero as this arithmetical operator. Also, just a notion of the modern scientific techniques that we can use to date things, which is of supreme importance, but science of this type doesn't trump all. Other historical considerations need to be taken into account to try and make sense of scientific processes, which may or may say something about the dates of these things. So, zero, we see it in the earliest cultures of mathematics in ways in which are familiar or unfamiliar to us, for which we get these little symbols that we have today. Thank you very much. So we've got some time for questions. Got a microphone coming.
Right. Okay, we'll start over here. So the girls will bring a microphone to you. So if you could speak into the microphone, thank you.
Okay, thank you. That was an amazing lecture. Really enjoyed it. I was just wondering about the Chinese, where that fits all in.
That's right. And so that's not, I've yet to learn Chinese in its various forms. But there's the idea of, and it's a very, very interesting question in terms of one system of numeration that we find in China has counting boards where they put actually rods and units to signify numbers. So we ask ourselves, is the absence of any rods in the particular cell in which they organise it, is that enough for the concept of zero for a symbol? We get a bit obsessed with needing a symbol and saying if early peoples don't have a symbol, therefore they're in some way naive or don't understand the concept. But they very well, we find, China is a great example, just like we had the table in the ancient Near East which had no entries, just that in fact it's a perfectly good way and sophisticated way to understand zero. So yes, in China there are many things beside, but the one that pops to mind are these counting rods, and the absence of counting rods being this placeholder in larger numbers. Yeah.
Okay, questions? So down here, excuse me.
Thanks very much for that. The Mayan civilization and their mathematics, we can probably be pretty confident had no interaction with the other mathematics. Is that true? Is there any evidence of interaction or or lack of interaction between the other civilizations you described?
And this is my sort of point on the very last slide, is that what we find is that parallel insights in mathematics are more common than we think. For instance, we see the famous Pythagorean theorem, which almost certainly doesn't go back to Pythagoras. Most scholars are quite happy to settle on that now, appears in the ancient Near East. It appears in India in 800 BCE. It appears in others. So useful or necessary mathematical facts tend to pop up in one culture or another culture without us needing to say, oh, somebody was borrowing that or stealing that or trying to fob that off as their own. I think the Mayan case, which indeed, as far as I understand, again, it's not my speciality here, was quite an isolated case, and some of the forms of representation, of course, were not terribly portable. Some of them were, like the quipus, some of the lovely string figures that we have, which have knots on them to indicate numbers. Again, a string with no knots, 0, the absence of something, which is a perfectly good way to represent 0 as a placeholder and both as a marker. So indeed, you know, because the system of the vigesimal system required some sort of placeholder when you're getting big numbers bigger than 19, it's just natural and automatic for them. So quite happy for them to have it, but it doesn't necessarily mean that, you know, they're inspiring other ancient cultures at the time. So it's a very good question.
Okay, over here.
What's the basis of coming up with a system based on 6? Doesn't seem to be anything anatomical or
about base 60, the sexagesimal. Yeah, so
rather than decimal.
That's right. So decimal system, we seem to think, you know, it's a good way to count, right? We've got 10 fingers, you know, that makes sense. It seems to be hardwired into us as a physiological fact. We've got 10 fingers. Base 60 seems to have come from, so there are various explanations for it. In fact, the earliest forms of numeration were alternate bases of 10 and 60. So we have a symbol for 1, for 10, for 60, for 100, and so forth and so on. There are explanations that say that 60 is a great number because it's got a lot of divisors. 2 divides into it, 3 divides into it, 4 divides into it, 5 divides into it, 6 divides into it, not 7, 8, you know. So there might have been a sense in which there were many disparate systems of numeration, and some bureaucrat somewhere who just couldn't cope with all these accounts coming in different systems of numeration said, oi, hold on a minute, let's get some consensus here. I'm going to choose 60 because then I can easily translate your disparate systems to come together. That might be a just so story. Probably one that is a little more realistic is that it came from systems of weights and measures that were circulating at the time. So just like we used to have the imperial system, or we now have the metric system, the particular systems of weights and measures to measure things such as grain and mustard seed and barley, quantities that we have records that they were measuring and trading with, the 60 came from the ways in which they traded. Yeah. So we just don't know. Nobody wrote down why base 60. Again, it's a lovely speculation that we have.
Okay, over here. Sorry, can we just wait till we've got a microphone? Thanks.
To all those who created the number 0, thanks for nothing. And
thanks for nothing. Oh, great.
and
yeah.
and other diagrams and so forth, but they had, most of the 3 of them had interlocks on to prevent this, but the 4th one had no interlocks, so you divided some by 0. It went on forever until you pulled the plug out.
All right. Okay.
Yeah, very nice. Indeed, the binary system, of course, with its placeholding zeros and its 1, of course, is a great example of a system which has 2 glyphs to need to represent any number whatsoever, which just really shows in some systems of numeration you really need this placeholder, and in others you just don't need it.
Right. Any other questions? Yes, there's one down here, thank you.
Thank you very much for that talk, it was really good. Following on from that last question about division by 0, when was division by 0 first characterised? Do we know that? Because it's quite a fascinating mathematical limit.
It really is, and I suspect that here in the Sanskrit texts here, this is where we've got it for the first time as far as I know, explicitly encoded as an arithmetical operation. So we've actually got, in fact, in these special cases here, something divided by 0, the special case when you're multiplying by something by 0, but you actually keep it 0 multiplied because you may need to keep that place. The idea of something really, really small or needing to keep this for a later arithmetical operation seems to have come here, as well as finding what is 0 over 0. So even though they're not quite analytically and rigorously defined as modern mathematicians might like, it just goes to show there was thinking about these ways in which 0 might act as an arithmetical operator and the ways in which we might need to keep track of it. And this is particularly relevant when we look at planetary motion in ancient India, which was modelled trigonometrically. And so thinking about very small changes and the resulting amounts there, we have to think about dividing by these very small quantities and actually having the equivalent of taking the rate of change of these trigonometric functions, which of course we know nowadays is the derivative, so we have sines and cosines here. So this is the first time I can think of where division by 0 and multiplication by 0 more properly is actually formally explicitly mentioned, and they appear in Indian sources. So that's Brahmagupta has it, and he is in the 7th century here.
Now there's yes, just behind here. Thank you.
I'm glad that we don't have to use Roman numerals for all the complicated calculations and things now. I guess that if we were trying to send someone to the moon using Roman numerals, the paperwork would probably stretch to the moon.
Probably would.
So the zeros and the placeholding system that goes with it's very important. But when the West discovered the 0, which I think it discovered it from the Arabs in Spain, but how quickly did people adopt the new system? Because it must have been a lot easier, but very different.
So I think just, when you say when the West discovered the 0, actually it was when the Arabic scholars, introduced this Indo-Arabic system of numeration. 0 was just seen as a part of it. And it got adopted really quickly. It was very, very useful. But in that context, of course, that was that 0. People knew about 0 and used 0, albeit in slightly different guises, much earlier than that, which is the important point that I hope to convey. Yep, so not discovering the 0, but really taking the whole entire system of numeration, i.e. these 10 little symbols for which to represent any number whatsoever, just got translated right away. Yeah.
Right, perhaps there's time for just one more question, if there are any more. Yes. I think we'll make this the last one.
Yeah, I was wondering, is there some research on from an evolutionary point of view of 0? You have mentioned that monkeys can be sensitive to the concept of 0. How about other animals lower in the ecosystem?
Right, so I guess that's when I feel it gets in the realm of neuroscience and psychology, and we're not talking about finding a symbol or a word for 0 or using it within a mathematical system, but something more innate with us. Whether or not it's significant in our terms of thinking about the ways in which neurologically we're wired to think about magnitude and quantity and largeness and smallness and nothingness, I just really don't know. But, researchers, neuroscientists are out there are looking at this concept. I mean, you can imagine, depending on the experiment, you imagine you have a pile with no bananas and a pile with 50 bananas, where's your animal going to go if they're hungry? Is that a way to test our concept of 0? I just don't know. And I don't mean to make light of the experiments, but we've just got to be sure we understand what we're testing for here. Are we testing for this this hardwired ability of us to go where there's plenty versus using something, a symbol or a glyph as a placeholder, as well as an arithmetical operator, and when these come together in a fully semantically correct mathematical system. But it's a very interesting question. Yeah.
Okay, let's thank Clemency again.